we'll get started. We have identified, when we moved from one dimension to two dimensions, certain challenges or new things that we would find that we had not encountered in the one dimensional case, and new aspects of modeling the problem that came up because we are now dealing with two dimensions, and this something similar would be there even if we considered three dimensions. So, we looked at modeling curved geometries as a challenge. Then the geometry would have some holes, some fillets, some curves which we need to model, which was not the case in the case of one dimensional problems. We also noticed that finding the shape functions was tedious when we went to two dimensions the conventional way. So, we needed something simple and easy way of writing down the shape functions. Then continuity of field variable across the edges, because there are an infinite number of points on an edge. Now, it is not enough if only at nodal points the temperatures are same or field variable is same, but at all the points in between. And of course, evaluating double integrals etc. is going to be a pain. So, we proposed natural coordinates as a means of addressing all these challenges. Of course, natural coordinates by themselves would not be able to solve all of them, but gives us a platform based on which we can build some solutions. Okay. So, you should see it in that way. We proposed that the natural coordinates, for example, in quadrilateral elements could be a perfect square varying from -1 to 1, zeta and eta, whereas real physical world xy could be anything x1 y1 to x4 y4 for a quad 4 element. So, we needed to do this coordinate transformation. That is what we discussed in the previous class. So, we have seen how we could derive the shape functions in the conventional way of taking C0, C1 zeta, C2 eta, C3 zeta eta, substituting the nodal coordinates, making sure it gives you the coordinates of the nodes, rearranging the terms, all that we can do. But we said no, that is a very laborious process. When we started with natural coordinates, we said these have advantage, I can directly think of doing something. So, we proposed that looking at that element, can we use the characteristics of the shape functions and then directly write them down. So, we talked about what could be n1, n2, n3, n4. We looked at the characteristics. N1 has to be 1 when you substitute coordinates 1, 0 everywhere. Similarly, N2, similarly N3, N4, like that, whichever is the nodes, okay, even if you have more nodes. Okay. So, based on that, we were able to say you could probably look at the equations of the lines that intersect at the node and the equations of those lines which are not containing this node. It gives you a way to look at what are all the equations that are satisfied by the nodal points. So, therefore, you could directly by inspection write down the shape functions. Okay. And of course, the scale factor would have to be there, because the product when you substitute nodal coordinates of node 1 may not be equal to 1, you want it to be 1. So, you would divide by a suitable scale factor, divide or multiply. Okay. So, that was the approach we took, and we were able to derive the shape functions by directly looking at the equations of the lines. For example, for n1 we said it would be 2, 3 edge and 3, 4 edge. 2, 3 edge is zeta is equal to 1, that means 1 minus zeta is 0. 3, 4 edge is eta equal to 1, that means 1 minus eta is 0. So, I could just write the shape function to be 1 minus zeta into 1 minus eta. So, that nodal points 2 and 3 when 4 when I substitute, they would automatically satisfy this equation. When I substitute zeta is equal to -1, eta is equal to -1, it becomes 4. So, I wanted it to be 1, so I divided it by 4, the scale factor became 1/4. That is how we derived the shape functions. Is the process clear? Any confusions, doubts? Okay. So, we could get N1, N2, N3, N4 and so on and so forth. But then we faced a challenge ki if this is how nodal displacements are interpolated in terms of functions of zeta eta, then I need the derivatives in terms of strains for dou u by dou x, dou v by dou y and cross derivatives for strains in x and y, normal strains and shear strain gamma xy. So, how do I get the derivatives? We discussed the Jacobian. I went through the derivation of the Jacobian and we also wrote it down for a quad 4 element. We saw that it depends, it will be a 2 by 2 matrix always because we are relating two coordinates xy to two coordinates zeta eta. Then it depends on the particular shape functions that you use and the actual real world physical coordinates x1, y1, x2, y2 etc. and enter into the Jacobian. Okay. We also discussed that the Jacobian determinant would be in the denominator, therefore, elements that are badly distorted leading to poor Jacobian related issues would be there affecting the performance of the element. That depends on the mesh. Now, element is frozen, that means the shape functions part of the Jacobian is frozen once you chose the element. Now, how the mesh is created, that will determine how Jacobian will be for each of the elements in the mesh. So, some elements in some zone, when you are doing your course projects, when you are using a software to mesh a complex shape, it may happen that the shape is such that sometimes you would end up with badly distorted elements. When you have badly distorted elements, then in the calculations the Jacobian will suffer, the Jacobian determinant will come in the denominator and therefore your results from that mesh are likely to be poor. If you had changed the mesh with the same element, you are likely to have got better results. So, these are the checks and balances you must do when you are finally submitting the course project report. I would appreciate if you include some discussion on in the report, may not have time in the presentation, but at least in the report, how is the element shape, what is the quality of the mesh that you have got, such comments. That means you are become now a well trained user of a software rather than blindly using it, input diya hai, output aa gaya. It should not be like that. Okay, fine. Now, when we looked at coordinate mapping, I also mentioned to you towards the end of the previous class that you have curved geometries and therefore, if I am doing straight edge only elements, 4 node quadrilateral element with a straight edge and I have a circular hole in a structure that I need to model, then that geometry I will not be able to model properly. Even if I were to take a few elements here and there, you would notice that I have either subtracted some material or added some material, because I am not modeling the circular geometry of the hole exactly, because my element is straight edged. So, this is a problem that we faced. So, we need to think in terms of some kind of nonlinear transformation. That is the stage we were in the previous class, in order to be able to model curved geometries in the real physical world. In the mathematical world of formulating the element, doing the integrals and all that, it would still be zeta eta, it would still be that perfect square, -1 to 1. I am going to distort it to represent a curved element. So, what you would see in the mesh in the software that you are going to use for your course project, in the screen you may see a distorted geometry that you are modeling with fillet radii, curves, holes, whatever features. But in the behind the screen, in the formulation of the elements, the calculations that go, all of them would be transformed to perfect squares and then the computations happen. Okay. So, what we are trying to discuss is actually what happens behind the screen. Okay. Even yesterday we were discussing with myself and some of my colleagues, is it necessary to discuss so much about what happens behind the screen. We should be focusing more on how to use what comes on the screen. I am sure all of you are intelligent enough, smart enough that you know how to figure out using the software. It doesn't take much of a time to learn the with using the very advanced GUI features that we have nowadays. It is not difficult for you to go and click here and there and then get a good looking mesh and get some boundary conditions applied and get some results. So I would think maybe if you sit down tight over a weekend, you should be able to learn basics of any software package. But the point is about how good are your results? How do you ensure that you will get good results? Without understanding what happens behind the screen, you would not be confident about the results that you are getting out of the screen. So therefore, we are spending so much time to make you aware of how the formulation actually goes, where are the challenges in formulating. Of course, for some of you who are tackling really new problems, which we are not able to discuss in this course, new problems for your research or thesis or whatever, then you may need to formulate an element. Then you would need to know all the details that we are discussing in the class. You would probably start from scratch with some complex coupled differential equations or an integral formulation, and from there you would start. Okay. So, keeping all these things in mind, we are discussing the focus of the classroom discussion would remain to equip you with a deep understanding of what goes behind the screen of these popular software packages. But the course project that you are doing, which has significant weightage of assessment, is the time for you to learn how to use these software packages which have made finite element method so popular all around the world to solve a near real world problem. Of course, in 1 or 2 months of the course, you would not be able to solve a problem completely, but you should do some simplifications, and that simplified problem you should be able to attempt intelligently solving it, trying to apply the knowledge that you have gained. Does the solution make sense? Do you think it is correct? How is the solution changing if I changed the mesh, if I changed the element, H refinement kiya, P refinement kiya? How is the solution changing? Is there some other way that I can model this problem? These are things that you should be able to debate amongst yourselves as teammates in the course project and bring life to that course project. Okay. So now going back to this particular case that we are discussing, what is the kind of transformation I should do so that the real world problem is there, it is real, that I need to be able to model curved geometries, and we said natural coordinates gives us that tool to develop that. So we are trying to now see xy to zeta, can it become nonlinear transformation so that my computations will remain easy, integrations, double integrals will be evaluated between -1 and 1 over a perfect square domain, but the real physical world distorted element could be modeled. So that is the one natural solution would be, could I use a quadratic element? Okay, a quadrilateral element with quadratic shape functions, which is better than linear. So would it be possible that I could use you remember from our discussion on a quadratic rod element, the linear rod element had 2 nodes, and a quadratic one, it had C0, C1x, C2x squared. So we had to put 3 nodes, 1 node in between. So extending that logic, I would tend to think that a quadratic quadrilateral element would have nodes in between. For convenience, I have put them at the center, but that is not necessary. Okay, you could keep them elsewhere also, and that changes the behavior of the element in interesting ways. So those of you who are interested can explore those angles, but right now we would be concerned about keeping it in the center. That's easier. So in the parent element, in the natural coordinates zeta eta I am talking about. Now in the real world, physical element, each point would have a corresponding point, so there will be similar nodes. But now I want to see if the edge 263 I focus on, that is straight, zeta is equal to 1 in the parent natural coordinates. In the real physical coordinates, can it be a curved edge? By doing some quadratic transformation, x and will be given, x and y will be given in terms of zeta eta, zeta squared, zeta eta product terms like that. So therefore, I am able to distort a straight edge to a curved edge through this nonlinear transformation. Would I be able to model an arbitrarily curved real world shape? Maybe not. This is better than the straight edge that I could get through linear transformation of a quad 4 element. If I were to do cubic element, it would be even better. So this is the P refinement model we are talking about. Yesterday's class I mentioned about possibility of doing it using H refinement. I use quad 4 element only, 4 noded quadrilateral quad 4 element. So linear shape function, straight edge will remain straight edge, but I would use Hazard straight edge elements. So I am able to approximate the curved shape better and better and better. But other alternative would be P refinement. So can I do this? So for that I need to get first the shape functions. So this is going to be an exercise for you now. What would be the shape functions for this? How many shape functions will be there? 8 shape functions. Anybody has any doubt that there will be 8 shape functions? There are 8 nodes, so there will be 8 shape functions. And I am not interested in writing down C0, C1, C2 like that, finding out, substituting, rearranging, no. Now we have left that part, okay. So now we are going to see if I can use the characteristics that we discussed in the previous class and reviewed in today's class. Can I find out what would be N1, for example? By looking at the system, can I write? What should be N1? N1 should be 1 at node 1 and should be 0 everywhere. So if you were to picturize this, it would look like this, correct? It would be some kind of a surface. So N1 is 1, then it has to be 0 at all other nodes, okay. What would be that kind of a function? Based on our discussion in the previous class, that you look at the equations of lines. So node 263 would satisfy the equation of line edge 263. And what is that? 263 is 1 minus zeta equal to 0, correct? So how would you write down N1? N1 would be some kind of a scale factor. I don't know the scale factor yet. What would the other terms be? Pardon? Square, no, square or not we will see later. It would be product of some terms, right? What would be those terms? Okay, 1 minus zeta. 1 minus zeta will take care of edge 263. Then 1 minus eta will take care of 374, it will take care of, because that edge is eta is equal to 1 or 1 minus eta equal to 0, okay. But then we have still 5 and 8. 5 and 8 is what? Multiply by zeta, multiply by eta, okay. So now what he is suggesting is okay. Any other suggestions for 5 and 8? 5 and 8 are lying on the axis, so he suggested zeta and eta. Okay, fine. I could have looked at the equation of 5, 8 line. What would be that? Huh? So it would be, you could have written, say, is that okay? Zeta plus eta is 1, is that okay? 1 plus, is it? I should put plus. Okay. Is that okay? So what we are now doing is to write by inspection, so to say. Now what his element shape functions and somebody else's element shape functions could be therefore different. This process that we are doing has no systematic basis. That is why these shape functions are called serendipity shape functions. Serendipity, I think it is. I hope it is correct. Serendipity, I mean, you are just looking at the system and then you think, oh, let me use this. Okay. Now, if you spend some more time, maybe you will come up with other ways of writing down these shape functions, okay, which could be same or somewhat different also. But each of these would then mean the rest of the formulation steps will be same, but the details will be slightly different. The element level equations will be slightly different. It is not that one is right, one is wrong. It is just that the shape functions being different will have different characteristics in the solution behavior and so on. So one should be aware of. Okay, fine. So I have picked up this. I don't know how. One, is that making sense? Yeah, all are minus, all are all plus. That's okay. Now, when you substitute the coordinates of node 1, it should be equal to 1. So the scale factor will get determined based on that. Okay. So in this case, node minus 1, so 2, 2, 4, minus 1 into minus 1, so 1, so 1/4, like that. Okay. Now when you expand this, I want you to look at what we got. Okay. So if you expand it, you will get some zeta constant terms, zeta eta terms, zeta squared, eta squared, then zeta eta. Okay. So if it is a complete quadratic polynomial in x, y or zeta eta, so it should have been C0, C1 zeta plus C3 zeta square plus C4 zeta eta plus C5 square. This is the complete polynomial in zeta eta, 2 coordinates, correct? But what we have got there, we have got additional terms like in, as I have marked in the triangle with a diamond shape. So zeta squared eta and zeta eta squared, these are 2 additional terms we got. If you expand this, I am not sure what you would get. You may get similar terms or something else. Okay. So it is possible. The reason why I am explaining in this manner is that, so you are when you are using your own intuition to come up with certain shape functions, not following the systematic method, because that was laborious, tedious, so we discarded that method. Okay, that would lead to one unique set of shape functions. Okay, but we discarded that, and we are trying to now, just by looking at it, by looking at some product of equations like that, we are trying to simply write down. So there could be different terms that you would include and different terms that you would exclude. So therefore the behavior will be different. The caution or a suggestion in when you are doing something like that is to make sure that you are symmetric about the center line. So if you have included zeta squared eta, you also would like to include zeta eta squared. So it is not biased towards any one particular coordinate. That is all that you can try to maintain at least. Okay, but we would see that certain additional terms have come in beyond the complete quadratic polynomial. It is not necessary that all the additional terms have come, then you would have got zeta cube and eta cube also. But when you can guess now, if I were to think in terms of a cubic shape function to approximate the curved element geometry even better, then I would have zeta cube, eta cube, but then this diamond will go even deeper down. So I will have even higher order terms, but total would be zeta cube, eta cube, everything included, but plus extra terms. This is something I wouldn't be able to really avoid. Okay. Try to maintain that they are symmetric about the. Now let's see. All this is fine. Actually, how well can I model a circular hole? Because a circular hole is something that is very commonly seen in geometries, right? Or a rectangular hole. Rectangular hole, so modeling is easy. Only the curves and chamfers at the end will be the problem. That will also be a circular arc. So basic element that we can think of is how well can I model a circular arc. So let's take, you can explore that in your weekend more deeply, but for the present purpose I would like to focus on just one edge. Okay, one edge, say 263. Okay, I would want you now to find out n2, n6, n3, and in the real physical world on a circular arc. So x2 0, 0, y3, let's say 1/4 of a circle. It's too ambitious. With just one element I am trying to model a quarter of a circle. It's not a great idea, but just to get an idea of how well I will be able to do. If you want to complicate it, you can take only a 5 or 10 degree sector or even a 1 degree sector, but then the coordinates would become some odd numbers. So I have chosen x2 0, 0, y3, and then you can choose somewhere x6, y6. So this is the exercise you are going to do now. Please attempt it. Write down n2, n6, n3, and then choose some coordinates. Okay, before we do the exercise, let's do a thought experiment. If I choose x6, y6, how would it affect? Why are we talking so much about choice of these nodal coordinates? If I choose x6, y6, x2 0, y3 0, y3 are the two edges, two nodes at the corners. Now x6, y6 is the fellow. Where do I place that fellow? Would it affect this transformation? Yes or no? Yes or no? I don't hear. So how many of you believe that locating x6, y6 would affect this transformation? 3, 4, 5. Okay. How many of you feel it will not affect at all? Only one. Why do you think it doesn't affect? He just feels it. It won't affect. And the rest of them are not here. Physically they are here, but mentally they are not here. Okay, let's go over it again so that I am able to get more of you to respond. Would the choice of x6, y6 affect this transformation? Do we believe that? Because I said choose. क्या फर्क पड़ता है? We should know that, no? Before you go ahead and choose something and actually do it. This is the trouble for us, even in the exams, midterms or whatever. When you see a problem, you just immediately get started to work on that. Don't do that. Take a minute to do a thought experiment. What would be the impact of the choice of S6, Y6 on your transformation? 2 and 3 are fixed on the axis. In this particular example, I mean, it's too ambitious an example, as I have already conceded. Modeling 1/4 of a circle with one element is not a great idea. Would it affect or it won't affect? How many of you think it would affect? Now, okay, some more hands have risen, but still there are many. How many of you think it doesn't affect at all? कुछ फर्क नहीं पड़ेगा. Still only 1 or 2 fellows now. There is one more. You have a friend here. In the front. 3. Okay. Why would it not affect?
Because the underlying relation between those points, like they remain on a arc and remains same to the future. Maybe modeling that won't change.
Okay. So let's 3 of you take 3 different choices. Anyway, you are sitting quite far apart, so you would not be able to communicate. So try out and let's actually see how the transformation would be. What is the limiting case of this transformation? Not a circular arc, let us say. I have a edge 263. If I were to take 6 in the real physical world to be halfway point between 2 and 3 in the real physical world also, what would happen? So, x6, y6 will be x2 by 2, y3 by 2, or x2 plus x3 by 2, y2 plus y3 by 2 basically. Then what would I get? Without doing anything, without putting your pen on paper, what do you think you would get? Huh? I mean, one edge would become a straight edge again. Is that much clear? If I were to take x6, y6 to be midpoint of 2 and 3, I would be reducing this to a straight line. Okay. So now you choose x6, y6 to lie on an arc of a circle somewhere on that arc. Doesn't have to be, as I have indicated, somewhere not 45-degree line or something like that, somewhere on that arc. But first you should find out n2, n6, n3 and then do this exercise. Okay. What is n2 that we get? Let's see what is n2 we get. N2 will be let me take theta eta, then it would be n6 will be n2, n3 I want, n3, so it would be 1 plus correct. These two are taken care of. Then it is right? Please check. I am looking at the figure and writing it out. It is not that I know or I remember anything. So N6 now, N6 would be the product of the three lines 3, 7, 4, 4, 8, 1, 1, 5, 2. 1, 5, 2 is eta equal to minus 1, so I put 1 plus eta. 3, 7, 4 is eta equal to 1, so 1 minus eta I put. And 1, 8, 4 is zeta equal to 1. So zeta equal to minus 1, sorry. So I put 1 plus zeta. Now when I substitute 6 coordinates, 1 and 0, so this is 0, this is 0, gone, 1, 1. So 1, so this would be, is it correct? Pardon? First, N6 or N2? N2 will be 1 minus zeta. N2, so we are trying to get the top line 1 minus zeta. Huh? So suppose I am looking at N2 or N6, let's say, easier one. So if I take product of equation of N6 I want, right? So 3, 7, 4, 4, 8, 1, 1, 5, 2. Okay? Is that okay? So product of 3, 7, 4 equation is what? Eta equal to 1. 1, 5, 2 is eta is equal to minus 1. 4, 8, 1 is okay. So now I take one plus zeta okay. Now I substitute the coordinates of node point 6 in this. Node 6 is 1 comma 0. So when I substitute 0, this becomes 1, this becomes 1. So no problem. Now this is 1, 1 plus 1 is 2, so 1 by 2. That's what I am explaining. I will now substitute coordinates of node 6. If I substitute in this coordinates of any other node, for example, node 1. Node 1, if I substitute minus 1, minus 1. So minus 1 means this will be 0. So this whole product will become 0. For any other node, it will be like that because that will satisfy the equation of that line. So no problem. Now when I substitute node 6 coordinate, which is 1 comma 0, I should get 1 because x should be equal to x6. Okay. So N6 has to be equal to 1 at that node. So I substitute 1, 0. 0 here gives me 1 into 1, 1. When I substitute 1 here, it becomes 2. So I have to scale it down by a factor of 2. N3. Okay, N3. Now let's see. Maybe, yeah. N3. Now where is N3? N3 is the corner, right? N3 is the corner vertex, right? So I take product of 3. So 481 then 152. So 48152, then 6 and 7 are there, right? 6 and 7 are there. So we have to put 6 is eta is 0 and this is, there should be a, okay, correct. That's what zeta eta has to be. Yeah. Whole equation multiplied by -1. Let's see. I mean, so we have to now substitute the coordinates of, are these individual terms okay? So now substitute the coordinates of node 2. Node 2 is what? Node 2 is 1 minus 1. So zeta is 1. So this becomes 2. Eta is -1. So this becomes 2. This becomes -1. So -1 over 4. Correct. -1 over 4. Because it has to be 1. X has to become x2 or y has to become y2. Temperature T has to become T2. So N2 has to be equal to 1 when you substitute node coordinates. This also may be like that, I don't know, check. No, zeta, it is 1 comma 1, so there is no problem. 1/4. Yeah, 1 comma 1 here, there is no problem. Okay. So like this, you can write down the shape functions of any element with any number of nodes by using this kind of a logic. Okay, fine. Now we have to use these shape functions. You are going to use some coordinates. So what should I take x2 to be? Say 4, y2 is 0, radius of a circle to be 4, let's say. So I am taking x2 4, y2 is 0, then x3 is 0, y3 is 4. Now tell me what would be x6, what would be y6? You know the equation, x squared plus y squared is 16, right? So what should I take x6, y6? Give me some nice numbers, if possible. I don't know if they will be nice. Under root of 8, under root of 8. Okay. So he is saying, let's take root 8. Root 8. Is that okay? X squared plus y squared has to be equal to r squared. That's the equation of the line. So root 8, root 8. That would be a 45-degree line actually. Okay. Fine, no problem. Now use x is n2 x2 on this edge. X is sigma ni xi, y is sigma ni yi, but on this edge all others are 0, correct? So edge 236 Okay. Is this okay? So x is what? N2 x2. X2 is 4, so 4 N2 plus x3 is 0, so this term goes off, plus root 8 of N6. Y is N2 Y2, Y2 is 0, so that goes off, 4 Y3, 4 N3 plus root 8 of okay. So you can now sit down. I would leave it to you for completing it in your room. Is the method is clear, right? So all of these are functions of, this is some function of zeta eta, this is some function of zeta eta. So you eliminate zeta eta, you will get this as a function of x relation some okay for edge 263. This edge 263, which is zeta is equal to 1, which is zeta equal to 1 in the parent element natural coordinates, would be transformed to some equation here. This will depend upon two factors. One is the shape functions and second is the coordinates that we choose. Okay. So the coordinates that we choose would affect it. Here, x6, y6 coordinates that we choose will come here and therefore they will affect that transformation. What is the equation you will get in terms of some function of xy equal to 0? That will be the equation of the curve 2, 3, 6 in the real physical world. Is that okay? If you find this a little challenging when you work it out in the room, you can go back and try this first, which was this one with straight line. This is fairly straightforward. With straight line, you can try what would be the equation of this line here. What is the equation of that line? So based on that, you can see how much material have you added in your model, finite element model, extra compared to that hole. Circular hole did not have any material. So this area, you can see this, the blue is the actual curve, finite element is the line. So therefore you have added this much material, which will shrink as you take more and more elements, and so that approximation would become better and better. What we have tried to do now also is the P transformation, which is I have gone one step further and made it a quadratic shape functions, interpolation functions. Is that okay? So this is how I would be able to actually use a nonlinear transformation between xy and zeta eta. My computations would remain over this parent element -1 to 1. Okay, so that is the advantage I am trying to get out of natural coordinates. So I would do the double integrals evaluation, limits will be always -1 to 1 for both zeta and eta. Okay, so that is the advantage I am going to retain for the computation purpose. With the real physical world, I will distort it and try to map curved geometries, boundaries. Still there will be discretization error. It's not something that you would be completely able to eliminate. There is a new error that has crept in now in our finite element modeling. You can actually try to see when you are doing your course projects, by plugging, easy way would be probably you may be able to think and come up with better methods. you could put some density to the material that you are using and estimate the mass of or volume of the CAD model or mesh that you have generated and actual object if you can get it, okay, you would see that there will be difference. It would not be exactly replicated in the finite element model. That is the amount of error we have introduced it now in 2D or 3D analysis, which is not there in the one-dimensional element. One-dimensional element was just a line, so there is no question of you were adding or subtracting some amount of material. So this is a new error, discretization error. I have still not formulated the element level equations, I have not still solved them. So the error coming because of piecewise continuous trial function solutions, because the unknown field variable, temperature or displacement or electromagnetic potential, whatever, is not varying linearly or quadratically within that element. That error still remains, we need to still figure it out. I have not yet formulated the element level equations, I have not assembled them, I have not solved them, I have not gone that far. I am now talking even more basic level, that there is a discretization error in the model itself. The model will not correspond to the actual system, which was not something that we encountered in one-dimensional problems. Is that clear? We are trying to minimize it by taking H refinement or P refinement helps us not only in modeling the unknown field variables variation accurately, वो तो है वैसे whatever happened with the one-dimensional problems, like we took 2 elements, 4 elements, 8 elements, 16 elements, 32 elements, the solution improved even with linear. Or we took quadratic and all that, then the solution again improved. So the field variables variation that is being captured better and better with H and P refinement, that's fine. But now we are seeing that it captures even the geometry better and better as we do H refinement, P refinement. So the discretization errors also will go down as we do H refinement, P refinement. So if you are trying out a simple problem, okay, geometry whose volume you would know, otherwise you can check the finite element and model and this fellow. As you increase the mesh, how it actually approximates the original. This becomes critical for systems when you have very complex objects being analyzed. For example, I mean, I don't know if there is any scientist from a lab. Say if you are working on an entire aircraft or an entire missile or ship or something like that. So if you are trying to model that in the organization, then different component sub-assemblies would have been modeled, analyzed, whatever, designed by different teams, okay, all around the world now. I mean, design teams are spread out. Now you are integrating all of these fellows into the complete system, okay, which is what you are going to experimentally test for its mode shapes, vibrations, temperature, behavior, whatever. So now even the how the components are joined together, sub-assemblies are joined together in the real physical system, whereas how you had modeled it individually and now you integrate them all, this complete missile's body mass and the finite element model's mass may or may not match. You see the modeling issues, challenges. Okay. When we go now from one-dimensional problem to 2D and 3D, the emphasis in one dimension was to understand the conceptual formulation of finite elements, that I am using a piecewise continuous trial function. First and foremost, I was trying to drill that into your heads. There is no complication about geometry at all, because it's just a line. But then The field variable, whatever it is varying, I am modeling it with bits and pieces of straight lines, quadratic curves, etc. I am trying to make it better and better and better and better. Now, when we come to 2-dimension, my first challenge is to model the existing geometry. Of course, as a novice, we would think that I should model 100% of the existing geometry exactly replicated into the computer. But as you gain more and more experience, you would start questioning, is it necessary? As I gave the example in the previous class, one of the classic ways in which we would do biomedical research is to take the X-rays, MRI scans, etc., and then recreate in the computer a model of the organ from all those images. So, there are now well developed software for this purpose. So, I am able to get, say, the femur bone, you want to get femur bone, you want to see, and how an athlete, as he or she goes through the sports, actually loads will come and so on. I don't know if any one of you has taken that as a course project, but if you want to model that. Now, how would you get a model of the geometry of the femur bone or a shin bone or whatever? Okay. So, you would take typical, the class, you could have taken all of your friends to X-ray room, taken the X-rays of all the 120 students in the class, and then developed an envelope of, individually there will be variations. So, an envelope of various parameters. So, when you go to 2 dimensions and 3 dimensions, now the modeling would be actually parameterized. So, you would notice in a package like ANSYS, you would have APDL, parametric programming languages will be there, features will be there, where you are able to design the volume of material to be modeled through some parametric shapes, some curves. You change this, you write it as a program, script file, and you keep changing them, you will be able to generate different models of the femur bone only to model better all the 120 students in the class femur bones. And that you extend it now to millions of people all around the world. How applicable will be your research results? You can't wait for everybody to fall, injure himself or herself, fracture. You can't do that. If you are trying to develop a rehabilitation device, prosthetics, okay, you may be working in rehabilitation engineering, right? So, you would not be able to do that. So, some people do experiments on cadavers. After somebody has died, you actually take out, cut it, and then take measurements and then try to model. But that is one person who has died. So, you will need to have some statistical models of various parameters to be able to accurately get the geometry itself. Okay. So, we wouldn't be able to in this course go further into those details. Those of you who are interested can look at that part, okay, explore it further. These are the challenges from extending what you are learning in the course directly to a real world problem. If you take up for your thesis or something, a biomedical engineering problem, suppose, then you would see this as a direct challenge. Extension is not obvious. You will need to do all these things before you are able to apply finite element model to that. Okay, fine. Any doubts so far, or are we doing okay? Please feel free. Okay, is that clear? Whatever we are discussing, what is the big picture kya hai? Then we keep shifting from plus 30,000 to minus 30,000 view of the subject always. You should always keep sight of that plus 30,000 feet. You are on a drone looking at the map of finite elements, how it is and all that. But at the same time, you will dive down deep, minus 30,000 feet. You actually need to know how the shape functions are, plus zeta, eta, whatever, so that you are able to actually do it. Okay. So, you should keep switching between these two layers. Then you would know how it is connected to other subjects and bigger picture kya hai, but actually how I will be able to do the analysis, both. Now, in simple logical extension would be, we are talking about now two things. One is the geometry modeling and one is the field variable modeling. I have focused right now to a large extent on geometry modeling. Now I will move over to field variable, temperature, displacements, etc. modeling, writing down the element level equations and so on. So, but before I go there, I would like you to do a thought experiment on these two aspects. It is possible that you are focusing the analysis on a section of the control volume which you have taken for analysis, where the field variables geometry is distorted and therefore the field variables are sharply varying. Okay. Say sudden change in the diameter of a pipe, fluid is flowing through. So you have a sudden step change which you need to catch in your model of the geometry. It would have some smooth variations, that fillet radii, etc. you would have put, so that what happens to the fluid, the turbulence that is caused because of the sudden change is minimized. So the field variable is changing sharply because the geometry is changing sharply, and how well you model the geometry smoothly would affect the results. That is one type of problem. Another scenario could be, yes, there is a certain change in the geometry, but that is not in a location where I am too concerned about the field variables. So there may be a certain elliptical hole or a circular hole or something like that, but at some corner which is not much loaded, so I am not worried about the stresses there. In the design, I do not expect this structure to be failing there. So that is not a critical design factor for me. So field variable there, even if I do not model it accurately, that means the variation is not steep, the values are not significant, it is not a critical location. But the geometry is, having circular holes, elliptical holes or whatever, sharp features. Sometimes it may happen the other way around. Geometry is fine, but you may have very high values of stresses because it is in the highly loaded zone. Field variable there has to be captured accurately. So when you are looking at these two things, sometimes it is necessary to model the geometry and the field variable accurately. Sometimes it is necessary to model the geometry accurately, but there the field variable is not important. Sometimes the geometry may be simple to model, but the field variable may be sharply varying. So the shape functions, why I am emphasizing these three extremities scenarios is that the type of element that I would use, the type of shape functions that I would use, because my only way of doing this is through elements and the shape functions, quadratic element, cubic element, linear element, the correspondingly shape functions. So sometimes I may use the same shape function for both geometry modeling and field variable modeling, or sometimes I might model the geometry with a higher order shape functions, but the field variable does not vary much, so I might use lower order. Or sometimes the geometry may be simple, so linear shape functions would be good enough, and field variable is sharply varying, I will need to use higher order shape functions for the field variable. So do not get confused between these two different problems. One is modeling the geometry, other is modeling the field variable. It is for you to decide in the problem whether a change in the sharper change in the geometry in the given location in your course project topic that you have taken, is that a significant feature in my design that I should be worried about. Failure will happen there, and I need to know accurately everything. Therefore, I need to use a very refined mesh there. Or, because if you go after every simple geometric feature to model accurately in your course project, you won't be able to solve your course project problems using your laptop. वो नहीं होने वाला है, because you would end up with too many elements. Some of you might have already encountered it if you had tried to solve a problem. So it is for you to understand this distinction. So I would be focusing on isoparametric formulation, iso meaning equal. So I would be focusing on this, but you should be aware that you could have subparametric or superparametric formulation also. It is just to reduce the confusion, I would choose isoparametric for the classroom discussion. Is that okay? Fine. Now, so far I have talked about quadrilateral elements, but the other element that we would have extension, natural extension from a linear element, a straight line linear element that we have talked about, rod element for heat transfer or structural mechanics or whatever, is to make it a triangle. Okay. So, in terms of triangular elements, I mean any other shape could be made up of quadrilaterals and triangles. So, there is no problem. So, if you look at triangular elements, the natural coordinates are defined slightly differently, because the reason why we are defining the natural coordinates in a particular way is to gain some advantage in terms of the computations. So, the natural coordinates in quadrilateral elements were defined to be over a perfect square of size 2 by 2. So, the variables zeta and eta are changing from -1 to 1, -1 to 1. Here, I would try to define it with the -1 to 1, it becomes a little complicated because you have a triangular shape. So, for triangular elements, the natural coordinates are defined in terms of what is shown in this figure, each of them varying from 0 to 1. How are they defined? You think in terms of any point P, it would now have 3 natural coordinates, L1, L2, L3. Even though it is a 2-dimensional problem, it should only have x, y, zeta, eta kind of coordinates. In the real physical world, yes, it has only 2. But in my mathematical world, where I will do all the formulation, I will have actually 3 coordinates. Obviously, not all of them can be independent, right? Because they have to be, there can only be 2 independent coordinates in 2 dimensions. So, the way in which it is defined is L1, L2, L3, you please see, you join, imagine that the point P is joined with the 3 vertices 1, 2 and 3, and look at the areas. So, L1, if you are looking at, it would be the area of the triangle P23, opposite to that vertex. That chota triangle P23, that area divided by the overall area. So, why I define it like that? When P becomes coincident with 1, then these 2 areas merge, it would become 1. L1 will be equal to 1. If P merges with, is coincident on either 2 or 3, that area becomes 0, and therefore L1 at node 2 or node 3 will be automatically 0. Is that making sense? Clear? Are you able to visualize that? Similarly, L2, L3. So, because of the way in which we defined and we said that it can have only 2 independent coordinates, L1 plus L2 plus L3 equal to 1. Okay. Because once you put L1 plus L2 plus L3, all the 3 chota triangles area is added, that becomes a total triangle area, and therefore the ratio is equal to 1. So, if you define L1 and L2, L3 is automatically fixed for any point. Okay. So, now for a 3-node triangular element, you already have the shape functions actually. X is n1, x1, n2, x2, n3, x3. n1 has to be 1 at x1, 0 at x2 and x3. So, therefore, it is actually L1 itself. Is that okay? So for a 3-node element, one, two, three, x of any point P is n1 x1 plus n2 x2 plus n3 x3, correct? Now when I substitute x is x1 coordinates, n1 should be equal to 1, all of these should be vanishing and so on. That is our requirement of the shape functions. So this, if you look at L1, what happens to L1? L1 is 1 here and 0 here, L1 is equal to 0. So N1 is actually L1, N2 is L2, N3 is L3 itself. As simple as that for the shape functions. Is it okay? In terms of natural coordinates, compare it to what we had to do. Let me see if I can quickly go back to that slide. How you defined the 3-noded triangular element in the beginning. So if we wanted to get the shape functions in xy coordinates, we thought of C1, C0, C1x, C2y. We substitute the coordinates x1, y1, x2, y2, x3, y3. So we get 3 equations, okay, and then we invert the equations, find out C0, C1, C2, and then substitute it. Then these shape functions became like this, where alpha, beta, gamma were given in terms of these variables and 2 delta was the determinant as follows. Whereas in terms of natural coordinates, I am able to just write down n1 is L1, n2 is L2, n3 is L3. Simple. So that is why I was saying of the challenges that we found, we are able to address them using the challenges that we have identified in one of those classes. We are able to address them using natural coordinates. It's easy now to write down the shape functions in terms of these natural coordinates, but nothing is free. So if you look at this as an advantage, the disadvantage we had is that I am interested in the derivatives in xy coordinates, but now everything is in terms of zeta eta coordinates or L1, L2, L3 coordinates. So I will need to relate these derivatives to those derivatives. So in between, lot of maths came in, Jacobian came in, okay. So there is extra penalty we have to pay there. So somewhere we gain something, somewhere we lose something, okay. So let's see how I would extend it to higher order element. So if I wanted a higher order element, quadratic shape functions, okay, curved edge triangular element, then I would need to put one node somewhere in between in each edge. So I have a 6-node triangle. So I apply the same logic, n1 has to be equal to 1. So I have a parent element triangle 1, 2, 3, 4, 5, 6, and this is transformed to some real physical element 1, 2, 3, 4, 5, 6 in the physical xy coordinates. Say let's say x1, y1 to x6, y6. Okay. So if I want to get x as sigma ni xi, y will be similar, field variable will be similar, and so on. So if I am looking at n1, n1 has to be equal to 1 at node 1, okay, and 0 everywhere. So by our logic, we can say that the equation of line 2, 5, 3 will be satisfied by the coordinates of the nodes 2, 5 and 3. So I can take product of equation 253 and equation 46. What is equation? Of course, some suitable scale factor. What is equation 253? What is this line? How are our natural coordinates defined? For any point P, you would imagine to be joined to the vertices, and this is your L1. Now, as P approaches this and lies on this edge 253, what would be L1? 0, because this area shrinks and becomes 0. So, this is actually equation of the line is simply L1 is equal to 0. So, this I will write it as simply L1. Now, what is the equation of line 46? Line 46 what happens if P comes here all the way to 1? So, L1 is equal to 1 here, L1 is equal to 0 here. What is this? Because these are midpoints of these edges, L1 is equal to half. Okay. Or two L1 minus 1 is 0. That's what I have taken there. 2L1 minus 1, equation of line 46. L1 is equal to half. Okay. So, it is so simple, straightforward to write down the shape functions. Okay. In fact, N4, N5, N6 become even easier. If you want looking at N4, it is equation of this line into equation of this line. This line is, what is this line equation? L2. This is L1. So, L1 into L2 multiplied with a suitable scale factor. Okay. So, you would be able to write down the shape functions in terms of natural coordinates fairly straightforward. This is still a kind of in serendipity shape functions. We can discuss later if time permits other methods of deriving shape functions in a more systematic manner and so on. But this gives you a handle, one way of writing down the shape functions very easily and then develop the formulation from here. And exactly what we discussed for the quadrilateral element, you can think of this, what would be the equation of a straight edge 253, how much you can distort it to get this curve. And if I were to model a circular hole, arc of a circle, how is this distortion happening and how am I able to get that curved shape? And if I increase the number of quadratic elements, will I be getting better and better, closer and closer to a complex shape? Is that okay? So, we would stop here. Okay. Any doubts? Okay.